Okay. Now what happened in the last lecture is that somehow I realized that the screen, my recording just got abruptly cut off at this location. So anyway, I've gone ahead and I've solved this problem. So the integral of dp by rho, and you, instead of dp, you can just put in the equation of state, and then you, this T naught is, so the question was for an ideal gas with isothermal conditions. So you can just take the T naught out and you have d rho by rho, and this is a simple integration from there. Okay, so this is where we stopped, where we were supposed to stop in the last lecture. So now what I've done for your next class is I have gone ahead and I've solved a particular problem for you, and I'm just going to give you this again as a sample problem. Again, this problem is already solved, and so I'm just going to quickly go through the solution and explain it to you, and we can go from there. So here the problem states that we have a water tank which is open, okay, and on this open water tank you have an initial water height of h, and gravity is going down, and here the area of the orifice is A at 0, okay, and let's say y is downwards, okay. So this is opposite to the general direction we usually take y, but here this water is flowing out of the orifice, and you have an area, a certain area here, and you have a certain different area over here, right. So the question is that the height of the water is being kept constant by a supply of water, say, or however it is being kept constant, and a jet is emerging from the bottom, and the cross sectional area of the jet is a function of the vertical height y. So let's say that in this area is known, because this is equal to the orifice area, height is known, y is known, then we are being asked what is ay in terms of obviously the other variables. Okay. So we solve this particular problem, and the first thing we do is to apply the conservation of mass to this entire control volume. Sorry, not entire control volume. First you have to define what the control volume is going to be. So what we do is, first we define this particular control volume right here. Okay. So this is just enclosing the jet. So then this is the equation for conservation of mass for a control volume. The first term can go to 0, assuming a steady state flow, and then you have the second one, and there are two fluxes in and out of this control volume. It leads to a very straightforward calculation where u2, which is the velocity at this point number 2. Okay, just 1 second, I don't think I explained this. So what I've done is I've taken a streamline from an arbitrary point on the top height that goes through this, and here is point 2. Okay. So so you have this simple relationship comes up. By the way, the fact that we are applying, we can take a streamline like this is quite interesting, because it's basically this flow which is happening, and the fluid is being drawn from all sides so that it can go into the stream. So there would be some particle that would be starting at some location here, and which would eventually travel down the jet. Okay. So you apply Bernoulli's equation between 1 and 2, and even 0, right. So 0 is this height right here. Okay. So 1 is this, and maybe I just mark 0 here, maybe it will be easier. Okay. So I might mark 0. So then you can apply Bernoulli's equation between 1, 2 and 0. Okay. So we have these three terms we have equated. Now just see that this last formulation that you have, we have a minus sign here because we have the particular orientation of y that we have taken, we have accounted for that, and then we have a minus rho gy. Okay. So 1, 2, This is evaluated at point 1, this is evaluated at point 0, this is evaluated at point 2. Now the pressures at all these different points, P1, P0, P2 is going to be P atmosphere, because P1 is obviously open to the atmosphere. P2 is also a force, a pressure that is there here, which is an open stream, it's an open jet. So the velocity, this pressure is equalized with the atmosphere, and similarly at 0, okay, which is just outside of this orifice. Okay. So using that, and at U1 is almost 0, Y1 is minus H, Y0 is 0, Y2 is H. If you use all these, then you get this familiar expression U0 is equal to root over 2gh. Okay, this is obvious. I believe if I ever took the interview of anybody, I might have asked this question in the interviews, because this is a very interesting problem. But this many people get, but when you want to when you expand the jet and just keep on going down, then this relationship not everybody is able to easily figure out. So now you have A2 by A0 is going to be this quantity, and that you can get by relating this and this over here, and using all the different the values of the different variables, you plug it in, and once you plug it in, these are the related equations. Once you plug everything in, you will get this. Okay, so once you have that, you obviously have also U2. Okay, so I'll just give you this problem, and you can take a look, and you can go ahead and try to solve this yourself. Okay. So now we are left with one another very important issue in vorticity dynamics, and that is the theorem of Kelvin, Kelvin's theorem. Okay. And it states basically that in an inviscid flow of a fluid, which means obviously that we are going to use Euler's equations. So in an inviscid flow of a fluid with constant density, or a fluid where the pressure is a function only of density, and where the only body forces, so I am writing down everything and we will quickly convert this into mathematical statements, and the only body forces are conservative, the vorticity of each fluid element is preserved. Okay. So to prove this, so this is what we have written in words, and we will see what the mathematical formulation of this becomes. So let's start with the first thing, which is we have an inviscid flow, right? So we will write Euler's equations. So Euler's formulation is valid, will be taken, and I am going to just write this in index notation. Okay, but this is easiest solved in index notation. So dui dt equal to minus 1 by rho del p del xi minus del g del xi, right? And why is this of this particular form? Well, we have already said that we are going to assume a conservative force, right? So, or okay, let me do this. Let me just replace it with minus Fi at the moment. So, this is my conservative, this is my body force, and then what we are saying is that it's a conservative body force. So, Fi is going to be equal to some minus dg dxi. Okay. Good. So, we have so let's just go ahead and replace that here, or okay, we can do that later. Okay. So, now that was the one important assumption. The other is that the pressure is a function only of density. Okay, so the pressure P is a function of only density, and this kind of fluid is called a barotropic fluid. Example could be a fluid would be of a fluid like this would be an ideal gas undergoing an isentropic process. Okay, so so there are those different situations in which this kind of a this kind of a formulation is valid. So now let us consider, as we were discussing an inviscid fluid where only body forces are concerned. So let us look at d tau, the circulation for a fluid element. Okay. So if since I have to look at the circulation of fluid element, I just the time rate of change of circulation of a fluid element, sorry, I am going to do a d, capital D here. So this is basically nothing but, and I have discussed what tau is. We have given the definition of that before, which was you take a certain curve and then you take this dot product and then you integrate over a closed curve, right? So now, so this actually is going to be equal to d dt of ui dxi. I've just, this is the dot, this is just the index notational form of the dot product, right? Okay. So, okay, just as a reminder, this is circulation, and we have defined this before. C is the contour, and the contour is not really specified, so it's an arbitrary contour, and u here is a fluid velocity. Okay. So now what we can do is, it so turns out that if you are looking at this particular form, and I am not going to prove this, but you can take this derivative inside. Okay. So this ddt. So my d tau dt equal to, now I'll take the I'll put this derivative inside. So I have dui dt dxi plus ui d of dxi dt, and this is simply the result of taking this thing inside. Okay, and then I just applied chain rule, nothing else. Okay, so let's see how to evaluate this. Now this is a complicated equation, so let's say, what is this term? This is a little bit of a funny looking term. How do we deal with this? Now we can just swap the derivatives. So we can just do a dxi dt here, and this is nothing but then so let us open out plus, let's say this is uj del xj, sorry, del xi, not del xj. Okay. Now this quantity has to be 0. This is related to the contour that you have drawn, right? So this term, the time derivative term, is gone, and this term is equal to sorry, just a second, this term, this term is equal to del ij, the Kronecker delta. Okay. So in fact this will become equal to dui. I hope you see how we got that. So now we go back. So what we have now is d tau dt equal to the integral over du I dt dxi plus dui, right? Okay. Now what is this? This is known to us. Is it known to us? It is, because we said that this is going to be the Euler's, the flow is inviscid. So this the dui dt term is equivalent to this. Okay. So let's just go ahead and swap that. So now we know that this has to come from Euler's equation. So if you do that, then you will end up with integral. Sorry, I realize that I'm changing the color quite a bit. Sorry about that. Minus 1 by rho del p del xi dxi minus del g del xi dxi plus ui dui. Okay, good. So we have arrived here. So now we need to in order to evaluate this, we need to evaluate this particular integral. Okay, that's all we need to do. So let's see. Now del p del xi dxi, what is this going to give us? dp. Okay. Similarly, del g del xi dxi is going to give me dg. Okay. And ui dui is nothing but the derivative of, since we are writing everything in terms of, see, everything here is becoming a derivative, so we want to make this into a derivative term as well. So we can just write it equivalently as this. Okay, so let's just go ahead and substitute it over there. What do we get? We have d tau dt equal to, okay, integral curve, this is minus dp by rho, yeah, minus dg, and then finally plus d half ui. Okay. Great. Okay, so I think that takes care of all the three terms. minus plus, yeah, okay. So this is nothing but I could, these are, you just evaluate them separately. Okay. Now this term is obviously 0. This is a conservative force field. So if you do a contour integral, that is going to lead to 0. So this basically this term is single valued in a sense. So this quantity is going to be 0, and similarly this quantity is also going to be 0. So sort of obvious. Now if rho were constant, okay, then you will be able to just take rho out and you have minus dp, right? But pressure is also a single valued function. So if pressure is a single valued function, then if you do an integral, this is a special integral because you are doing a contour integral, so you are doing it over a closed contour, this would go to 0, okay, if density were constant. Wait, so let me do just one second. Let me just simplify this. So d tau dt equal to, so unless people specify how rho behaves, you cannot really evaluate this. So that's why we are going to box this and say this is an important result. Okay. Now if density is constant, then this quantity is going to be 0, okay. Or if pressure, or somebody says that pressure is a function of only density, nothing else, then this will also imply that dp is nothing but this quantity, and this is nothing but some function of density into d rho. I am out of space here. Just a second. Oh. So this is some function of density that you can evaluate, and this is d rho. So if density is just a function of rho, then it is fair to write this dp as some function of rho into d rho. So then you will end up again with being able to evaluate this as a function of, so this will be basically some function multiplied by d rho integrated over a closed contour. And if density is again a single valued function, this entire thing is going to go to 0. Okay, so that again implies d rho. So therefore, the flow of inviscid fluid, okay, in conservative force field conservative body force field, and where density equal to constant, I'm just going to write it mathematically, it's easier, or p is just a function of density, okay, then vorticity of a collection of fluid particles remains unchanged, right? Then, and with respect to time, so then d tau dt is equal to 0, and this becomes the statement of Kelvin's theorem. Okay, So here it is important to note that this pressure is a function of variables other than when pressure is a function of variables other than density, the continuity integral need not always be 0. Okay, and as you might anticipate, the vorticity of a fluid element may be changed through the action of viscosity, non-conservative forces, or density variations that are not a function solely of pressure variations. So this is our statement of Kelvin's theorem. So let's just box this. Okay, and this is a very, very important theorem with regards to vorticity dynamics. Now in the book you have a discussion on vortex treat, I believe, and vortex. Just one second, I'll quickly take a look at it, and those are not going to be part of the syllabus as such, because I don't think you don't need to know enough about it, because to understand vortex sheet, it's just too early to introduce that idea, because you need to understand some of the other topics first before you go into vortex sheet. So that's why I'm not going to introduce it right now. Okay, I'm sorry, I can't find it right now, so we'll leave it at that. Okay. Okay, so now that we have done with Kelvin's theorem, there are a couple of other things that we have been looking at, and I want to go back to it a little bit. So one of those things was, I had asked you a few classes back. Okay, when we were looking at stream functions, we defined the stream function with respect to the continuity equation, and then we had asked you to show that the lines of constant psi are streamlines. Okay. I don't know if you have had time to sit down and look at it, but let's work it out today. Okay. Now, basically, a stream function is a very special function, and that is useful only for analyzing 2D flows. Okay. So let us go into stream functions one more time. And these are for 2D flows, and it satisfies the continuity equation, and we want to show you the stream function is constant along a streamline. Okay, and that's a very important observation. And the flow doesn't have to be, you don't have to do it in axisymmetric, Cartesian coordinate systems, but you can also define stream function in let's say polar coordinates. So for example, if you have a polar coordinate, then you will define the stream function in terms of r and theta. Okay, and then your ur will become 1 by r del psi del theta, and u theta will now become del psi by del r, and you have to put a minus sign so that all of them sum to 0. So you can again easily show that this satisfies the continuity equation in 2D incompressible flow. Of course, you have to write then the continuity equation in polar coordinates as well. Okay. Now let us come back to the point that we are looking for, which is stream function is constant along a streamline. So here let us try to determine the curve along which the stream function is constant. Okay, and let us take the case of incompressible flow in rectangular coordinate system. So your del psi or psi, so we are going to consider the Cartesian coordinate system, so we will just write psi equal to x comma y. Okay. And let us consider change in psi due to a small displacement dx comma dy. Then now what is d psi? Is the total derivative, and my psi is dependent upon two variables. So by chain rule it will be this particular quantity. And what is del psi del x? We have already defined this to be minus uy dx, okay, and del psi del y is ux, this is plus dy. So we want to determine a curve, okay. So the curve that we seek is such that psi xy equal to some constant, right, which implies d psi is equal to 0. Therefore, the curve that we are looking for is a curve such that d psi equal to 0 equal to uy dx plus ux dy. So this tells me that the curve is such that dy by dx, okay, such that psi is equal to some constant. If you want to keep this, then this is nothing but uy by ux. Do you remember this quantity? This is similar to streamline definition, or the same as streamline definition. So from here you can, it's obvious that you can now conclude that if psi is constant, then this has to be a streamline. So this is a very important assumption, understanding, okay, and this lets us work with a lot of different, it allows us to use stream functions to gain important insights into the problem. For example, if you were to quickly do an example problem, let's say that my psi xy and it's given in Cartesian coordinates to you, and this is equal to x comma y, where a is some constant. Okay. Then what does my flow look like? If I had to draw okay, and maybe this is not the right place to write this. Let's just, so this is a constant. If that is a constant, then what are lines of constant psi? That is given by some y equal to some constant k by x. Okay. So let's say psi is some constant. So if your psi has to be constant, then y is equal to, has to be some constant times divided by x. And what is this? This is a hyperbola, right? So the flow streamlines would look something like this. So the flow streamlines functions are hyperbolas. Nice and interesting. And let's just, for the sake of it, let's just go ahead and then complete my derivation of ux, which is, or the find out, let's just find out the values of ux, which is going to be del psi del y, and this is now going to be ax, and uy is equal to minus del psi by del x, and this is going to be minus a by y. Okay. So this is a good and important observation. So today we can just stop here, and from the next class onwards we'll look at a few other things related to stream functions and vorticity and velocity in two-dimensional cases. Okay, so let's stop here today. Bye.